All right. Our next speaker is Professor Tang Yuzhe. Professor Tang is currently an associate professor in the EECS department at Syracuse University, with research interest focusing on the cybersecurity and the computer system. And he is particularly interested in the blockchain security, threat detection, and mitigation. His work has been featured in top venues such as Using Security and ACM-CCS, and his contributions have led to updates in Ethereum clients like Gas and Bosu. He also founded the BADD Labs for blockchain and D-app development. Professor Tang holds a PhD from Georgia Tech and has received multiple awards, including the IEEE Cloud Best Paper Award and the Ethereum Foundation grants. He is a speaker at the Stanford Blockchain Conference in the year of 2023. Now let's welcome Prof. Tang.
All right. Good morning, everyone. Thank you for having me here. It's my great pleasure today to talk about the research we are doing in my group. So this is research on blockchain software security, particularly security of Ethereum under denial of service attacks. Here goes the title, Understanding Ethereum Mempool DoS Security via Symbolized Stateful Fuzzing. So my name is Yuzhe Tang. I am associate professor from Syracuse University. I advise the research group called Full Stack Security Labs. This is work with my student, Yibo Wang, former student Kai Li, Wang Ningding, and Zhihua Yang. Okay. The research I'm going to talk about today is related to one particular component in a large blockchain ecosystem, which is called memory pool. Let me start by introducing what memory pool does. Okay? So here we are looking at a super simplified model of transaction flows in the blockchain system. Transactions are typically generated, signed by Web3 users. And then those transactions are sent out to the blockchain network, first reach a component called memory pool. This is where the unconfirmed transactions are buffered. Okay? And then the validators are going to read the memory pool and select certain transactions to be included in the next block. Once the block is generated, validators are going to do this gossiping process as mentioned by Dr. Karami's talk. And then if a consensus is reached, that the new block will be appended to the chain or block or blockchain. Okay? So this is how it normally how the transaction flows. Okay? So in this workflow, what if the memory pool goes out of service, right? There will be some consequences. So first, the Web3 users will not be happy. Those Web3 users, they are usually, let's say, traders. They read the memory pool transactions and find some profitable opportunities, such as in MEV, maximizable extractable value, okay? And then they instantiate that MEV into transactions they are going to send. So if memory pool goes out of service, they will not be able to read those transactions from existing memory pool, but also the transaction they generate will not be able to made on the blockchain, because memory pool is done. Okay? What does that mean to the traders? So meaning that their profitability will be sacrificed. They will not be able to extract the value from the blockchain. So this is especially concerning because those transactions are time sensitive, right? So if you miss that time, then you miss the opportunity to get a profit. Okay. So what does it mean to the other actors in this workflow? Validators. Since memory pool is done, the validators will not be able to read any transactions. So their job, which is to pack those transactions into the next block, will also be damaged. For instance, they will be forced to produce empty blocks. So empty block, meaning blocks of 0 transactions in it, to the validators, they are most incentivized to get profit, get revenue from those blocks. One of the revenue source is the transaction fees. So if you are forced to generate empty blocks, meaning that the transaction fees, they will not be able to get any transaction fees. Okay. Of course, there is another source of revenue, which is block reward. So since in Ethereum, every 4 years, the block reward is going to halve, which is actually the case a couple months ago. The transaction fee will become increasingly more important. So validators producing empty blocks will not be get any revenues from that. Okay. So now we know that memory pool plays this critical role in the transaction workflow. Naturally, if it is done, it can create these severe consequences to the downstream actors. So the natural question we're going to ask in terms of doing research is, okay, this is a pretty important security aspect or attack vector. How practical is this attack vector? Okay. So given that memory pool is quite important, quite critical, our research result shows that surprisingly, this attack is super easy to pull off, and it comes at very cheap cost at the attackers. So particularly, we focus on this, what we call asymmetric memory pool DoS attacks, or ADAMs. Okay? Asymmetric in the sense that the attacker's transactions will not be included in the blockchain, and they will not need to pay any fees to victimize normal transactions. Okay. So there are some existing research in this field. One of them is Deter attack, which is published in CCS 2021, which is also from our group. And in Using Security 2024 this year, there's another paper, Memory Purge. Okay. So those attacks, they are super easy to execute, and actually on the testnet, on this screenshot here, it shows an actual attack incident during the similar attack. So the timeline, so this is a screenshot taken from Etherscan. So the timeline goes from upwards. Okay. Basically, each line is a block produced at a particular time point, and this column, wait a minute. Oh yeah, the last column here, gas used per block, which basically measures the gas utilization of the block. So there's a tiny percentage here, so the higher the percentage, the more full the blocks are. Okay, so here you can see before the attack, the gas utilization are almost 100%, 98%. Once this attack is mounted during these 4 blocks, they are dropped to almost 0%. 0%, 0.02%. And then after the attack, there are some residual effect, but the gas utilization bounced back. Okay. So this is the state-of-the-art research, but there are some limitations. One of the big limitations here is that those attack vectors are discovered manually on a client-specific basis. So what does that mean? Because in blockchain, software evolves pretty fast. Okay, so if we want to understand the DoS vulnerability of evolving client software. And what we have today is a manual analysis approach. It means that every time there is a new release, we need to invest human labor to inspect the new client manually or audit manually, and then do some analysis to figure out if there is any vulnerability or not. Okay. So this is, of course, does not scale. So what we want to achieve in this research is to automate this vulnerability discovery process. How we can automatically discover memory pool DoS vulnerability. So that's the research question we are going to address. So in terms of vulnerability discovery, one of our common approach is to do fuzzing. This is a dynamic analysis approach. So fuzzing is a promising approach to discover vulnerabilities. But there are some existing fuzzers designed for blockchains. But we are the first to address the problem of fuzzing memory pool particularly. And the memory pool fuzzing is quite unique. It's a different research problem that existing fuzzer does not solve. For instance, when you fuzz a memory pool, it's not about finding implementation bugs or crashes as tackled by existing fuzzers such as AFL and Locky. It's more about finding these design flaws. Okay? So how are you going to specify bug oracles? Also, memory pool input space, which is basically unlimited sequence of transactions, including invalid transactions. So this input space is quite different from the input space of other modules in a blockchain system. For instance, in consensus, you only take validated transactions. Okay, so that makes existing like a consensus fuzzers such as TYR inapplicable to our case fuzzing memory pool. Right? And also, this is not a differential fuzzing problem as tackled by Fluffy, because in quite a unique thing in memory pool is that it is totally fine that the two nodes maintains two different kind of transactions in their memory pool. Unlike a consensus, you have to ensure that the different nodes maintain the same synchronized state. Okay, so Fluffy, which sort of do differential fuzzing to find the differences between state across different nodes does not apply to memory pool. Okay. So our research problem is how we are going to fuzz real-world memory pool implementations, let's say in Ethereum clients, to discover asymmetric DoS vulnerability. So the solution we come up with is MP fuzz, memory pool fuzz. It is a symbolized stateful fuzzer for memory pool. So the essential design challenge here is the search space is pretty big. As I mentioned before, if we want to just use existing fuzzer, you have to basically search the raw input space, which is the unlimited sequence of transactions. Okay. So in the first design iteration, we sort of reduce that big search space using by formulating the problem as a stateful fuzzer. So we search the memory pool state of limited size. Like each memory pool has a limited size, not infinite size. So we don't search the transaction sequence space. But still, this is the same, still pretty large search space. We still need to deal with what is called state explosion problem. So then in the second design iteration, we come up with this essential idea, which is to symbolize transactions. Okay? So instead of searching concrete transactions, we're going to search symbolized transactions and the symbolized memory pool state. I will talk about what I mean by symbolization. Okay, so in terms of the design of fuzzer, So you have to use this basically 3 steps in terms of formulating the fuzzing problem. First, we reduce the original memory pool, for instance, from big space to a smaller memory pool. In Geth, for instance, each memory pool can take up to around 6,000 transactions. So we reduce the memory pool size to just less than 10 transactions. And this is what we call memory pool under test. And then we use what we propose for Symbolized stateful fuzzing on MUT to discover short, small exploit. Once we got this short exploit, we are going to extend it to the, from, let's say, 3 transaction memory pool to the 6,000 transaction memory pool. Okay. So our main innovation is in the second step. So this is how a typical stateful fuzzer works. Basically, in each iteration, you select a state from what is called a seed database, and the selection criteria is based on a metric called energy. And then, given the seed state, what you need to do is mutate the input, which is the transaction sequence. Okay, so we are going to instantiate a transaction symbol under the context of a current state. After that, send the transaction sequence to the memory pool under test, maintaining this initial state, ST, and then observe the end state, let's say ST prime, and then after that, if the end state satisfy the bug oracle, we are going to emit this malicious transaction sequence, triggering vulnerability. Okay. If not, then we check the state feedback and then add, if it is positive, then we add ST prime to the seed database. So this is an iterative process. Then we go back to step 1 or step A. Yeah. So this is how a typical stateful fuzzer works. And we sort of apply transaction symbolization in these 5 steps. Basically customize different metrics in these 5 steps: energy, mutation, bug oracle, and seed feedback. Sorry, state feedback. So in the next couple of slides, let me talk about how different metrics are customized based on the idea of symbolization. So first, how you're going to define bug oracle. I mentioned before, this is not about the triggering crash of your software. It's more about finding design flaws. And design flaw is application specific. So in this case, we do get our inspiration from the existing attack, deter attack. For that, let me briefly talk about how deter attack works. So the threat model here is super simple. Let's say, we all know like in blockchain, there are multiple nodes. Let's say in the simplest case, 2-node scenario. The attacker controls one node, while the other is the victim, where the target memory pool is located. So this attack node is going to send what we call future transactions. So if you are familiar with Ethereum, future transaction is a type of transaction that is currently invalid. It has a non-consecutive nonce with what is already there included. So the attacker is going to send future transactions to the victim memory pool, and the victim memory pool is going to accept it. Okay. And then, because the memory pool has a limited size, 6,000 transactions in Geth, so if the memory pool is full, which is very much the case today, so the memory pool need to make this difficult decision. If it needs to include this future transaction of very high price, it need to make room for that transaction by evicting an existing transaction. Okay, so in Geth, that's the case 4 years ago to 2020, 2020, sorry. So Geth made this pool risky decision to evict existing valid transaction and to make a room for an invalid transaction as a future transaction. So that's how this attack works. So we sort of abstract this concept and define the bug code that we call eviction memory pool DoS attack. Okay, so it has two essential metrics. One is first the attack. How can we say attack is a successful one? This attack first has to satisfy full damage, which means that given an initial state, the memory pool storing owning valid transaction, normal transaction, if it reaches an end state where the memory pool stores no normal transaction, then that we say that is that's one metric. Okay, but the difficult thing here is that in Ethereum or any public blockchain, there is no way you can tell if a transaction is a malicious transaction. Okay, so we come up with this metric basically if the end state and the initial state they don't have any overlap. Okay, and the other thing here is that the attack cost has to be low. Which means that for the end state, the total fee in the transaction divided by the total transaction fee in the initial state has to be smaller than a certain prefixed parameter epsilon here. Okay, so that's one bug code. Of course, we have come up with another bug code called locking memory pool DoS. Okay, so the essential idea in this work is to symbolize transactions. So our motivating observation is this. A memory pool is going to make the same admission decisions as long as it is a future transaction, for instance. And this decision is agnostic to concrete transaction construction, such as where this transaction is sent from, which account is it sent from. For instance, given two future transactions, one is sent from Alice, the other sent from Bob, the same memory pool is going to make the same decision for both transactions. And whether or not this transaction is sent from which one is irrelevant. Okay. And this is a very useful observation for designing fuzzer, because fuzzer you are going to cover a lot of transactions, cover the transaction space. So the implication here is as long as a fuzzer covers a future transaction sent from Alice, it's sufficient to cover that memory pool behavior. And there's no need to cover another transaction or search another transaction, another future transaction sent from Bob. Okay. So we instantiate this observation into what we call transaction symbolization. Okay. Basically, we are able to summarize this huge transaction space to search into just 7 symbols. Okay. Here, 7 symbols being normal transaction, replacement transaction, future transaction, parent transaction, 3 subclasses of child transaction, child, overdraft, and latent overdraft. Okay. And for each class or each symbol doing fuzzing, we just need to cover 1 transaction per symbol. Once that transaction is covered, there is no need to search any other transactions in the same symbol. So this gives us a huge speed up in terms of doing the fuzzing. Okay, so we materialize this symbolization design into different metrics, as I mentioned before, in stateful fuzzer. So the energy basically measures the symbolized cost of the state, and when we use state feedback to guide mutation, we use 2 metrics. One is symbolize the state coverage, and the other is we prioritize the state of fewer transactions. Okay, and the state feedback, both the design of state feedback and energy measures or realize this intuition, if it is more promising for the current state to reach, to trigger a bug oracle in the future, then that state will be selected for the mutation. Okay, so here let me quickly go through this example how this MP fuzz works. Basically, we are looking at each triangle here is a memory pool state. And here is just 3 transactions or normal transactions in the beginning, and each arrow here means transaction mutation. Right? We're going to try 3 different choices. Okay, so this is sort of a DAG or a tree, and if when you branch out, if there are multiple subsequent states, and if they are identical to each other in terms of a symbolized state, then they will be skipped. We are going to focus on distinct memory pool state when we grow this tree. Okay, so here in this tree generated, you can see initially the memory pool is storing 3 normal transactions, and in the end it stores a future transaction and 2 empty transactions. So this is the case that we find on Go Ethereum client or Geth, and in that case we find a successful attack. So we implement our fuzzer, and we did ablation performance study. Basically, we implement a bunch of baselines. And so starting from the stateless fuzzer, and we take out the different features from MP fuzz and measure their performance. So here, under 2 settings, 6 slot or 6 transaction memory pool running with time budget 2 hours. You can see with the baselines, the fastest baseline is 1 minute, but our approach is 30 milliseconds. Okay. Of course, when you want to scale out, this the time difference is pretty significant. Okay. So that's one. On top of that, we also use our MP fuzz to find vulnerabilities in the latest Ethereum clients. In 2021, when we published this paper in CCA's Deter attack, Ethereum Go client decided to adopt our mitigation proposal in that paper. So the Deter attack is sort of fixed. And we want to know that even though Geth has fixed this Deter vulnerability, is there any unknown vulnerabilities in the latest Ethereum client that is already patched? And surprisingly, we find many of them vulnerable under MP fuzz. So it's blurred, but you get the sense almost all the Ethereum clients, they are still found vulnerable under MP fuzz. And for the 2 different bug oracles, eviction attack and locking attack, we do find new patterns. For instance, for eviction attack, we find this turning-based attack pattern, which, unlike previous Deter attack that just finished the attack in 1 single step, this one consists of multiple steps of doing state transition to reach the vulnerable end state. Here, let me quickly go through one example. So in this super simple example, we are looking at a 2-slot memory pool of buffering just 2 transactions, 1 and 2. They are sent from the same user, Bob, and their nonce is consecutive, 1 and 2, which means that they are both valid transactions. Price-wise, the same price 3, and the value means how much ether is going to be transferred. Okay, so in step 1, the attacker is going to use his account, Malloy, to send another 2 valid transactions. Okay, in Deter, they send invalid transactions. In this case, send valid transactions, 1 and 2, and these 2 transactions, 3 and 4, basically have the same price, but the price is higher than the price of existing transaction there. So what is this memory pool, victim memory pool going to do? Of course, is profit-driven, is going to evict the transaction 1, 2 to make room for transaction 3, 4, right? Because it's more profitable. After that, so the attack controls the memory pool right now. And then it starts to do this second step, which is to send a replacement transaction. A replacement transaction in Ethereum means that it shares the same sender and announce with the existing transaction that he sent before. In this case, TX5 has announced 1 and price 5. So this is a replacement transaction for transaction 3, 1 and 4. Okay? So the memory, since 5 is 10% higher than 4 in gas, so that transaction will be, TX1 will be replaced. Oh, sorry. So the transaction will be replaced, but here, TX5 has a value 5, while transaction 3 has a value 1. What that means is that if Malloy's balance is just 5, this means that in this new end state, transaction 5 is going to deplete the balance in Malloy's account. That makes TX4 an overdraft. And the overdraft is prohibited in Ethereum, in any blockchain. Okay. So this is sort of turns the existing transaction TX4 into an invalid transaction. That decreases attack cost. So of course we test our the vulnerability on testnet is the same screenshot, with a similar format as I showed before. So you can see the gas utilization drops to just 3% as before. Okay. So in this whole process, we report our bugs to Ethereum Foundation, and we appreciate their support in terms of 3 academic grants awarded to my group, and also we are supported by 2 National Science Foundation awards. So you can find the bug report online with this QR code, and this is the paper published in Yuzhe Security 2024 in Philadelphia just 1 month ago, and we open source MP files in this link as well. Our software artifact has passed the artifact evaluation in Yuzhe Security 24. So this is the last slide. The limitation of MP files. So first, MP fuzz is actually, if you remember these 3 steps, reduction during the fuzzing and then extension. So step 1 and 3 are not fully automated. I would say if we want to fully automate this whole workflow, there's still a gap, and that defines open research problem. The other thing is MP fuzz right now is designed specific to Ethereum. Okay, how we can sort of tailor it for other blockchains, Solana, Bitcoin. Beyond the Ethereum, that's an open problem. But the more grand challenge in this space is how you can design provable memory pool DoS security. Okay, so this is a big problem in the space. First, how you can specify memory pool security formally, and then how you can prove an existing memory pool is secure under that specification. So in that direction, so there's actually, we just told that there's a paper accepted in Oakland next year, 2025, from our group, which sort of take first step towards that grand challenge. Okay, with that, thank you very much for your attention. Open for questions.
Thank you. We can take a few questions if you have.
Thanks for the nice talk. First question, what is the false positive, false negative rate for your fuzzer?
So I would say, since this is a fuzzer dynamic analysis, we don't guarantee 0% false negative rate. But in terms of false positive rate, I would say it's 0. Because in our case, remember, we do these 3 steps, and eventually we validate the vulnerability that we discovered on the original memory pool. So in that sense, it's always reproducible.
Okay, thanks.
Thank you for the question.
Last question. You said that, I found this fascinating. You said that this is a great mempool for fuzzer for Ethereum, but for other blockchains, the other issue might arise. Is it really Ethereum specific or is it EVM specific?
So this, I would say this has nothing to do with smart contract execution. In our model, we don't cover that the data field in
But you're looking at gas usage. So
I would say it's not relevant. Gas usage is also relevant to smart contract execution. So it's a sort of a generic transaction model that can definitely applicable to Bitcoin, where you don't. So basically, you don't need to execute a smart contract.
Super.
Okay, thank you. Let's thank Prof. Tang again. Okay. Let's thank the 2 speakers again, and this concludes the end of the security session.
Thank you for all the speakers to share their insights on security. Now I would like Prof. Wen to facilitate Prof. Goss and Prof. Tang on the stage. We are going to have a lunch break now of around 1 hour, and we'll be starting session 3 on consensus and networks around 1:30 p.m. So yeah, VIP and guest to the left, and general audience upstairs. Thank you.
For the speakers, you may use that room to go into the lunch place, and for the participants, you can use that room, the door to the lunch